Hi, I'm Yuan from University of Southern California. I'm presenting our work titled Accelerating Monte-Carlo Research on CPU-FPGA Heterogeneous Platform. I'll start by introducing some context of our work. Monte-Carlo tree search, or MCTS, is a reinforcement learning algorithm that combines a best first search tree guided by random simulations to find a sequence of optimal decisions in a system. It's successfully applied to solve many real-world AI benchmarks with large search space, including classical control, robotics, games, and neural architecture search. In these benchmarks, an agent explores a world we call the global environment and is required to take an action in each step. To decide an action, the agent uses an internal policy model represented by an attributed decision tree. The tree is constructed by one or multiple workers that serve the agent. These workers interact with local simulation environments that mimic the behavior of the global environment, and they use the collected statistics to collaboratively construct the tree policy. The tree policy is composed of a set of nodes and edges. Each tree node I represents a state. It has three attributes. N represents the number of visits to node I, V is the average reward obtained by visiting node I, and the state represented by I. Each edge, ij, represents an action used to transit from a parent node I to a child node j, and the weight of the edge is the UCT value computed using the equation in the box. This value denotes the chance of the action to being selected. The first term is an exploitation term, that is, the expected reward for visiting the child node j. The second term is the exploration term, saying that there should be a higher chance of visiting child node that has lower number of visits. So C is just a term controlling the trade-off between the exploration and exploitation terms. In an MCTS iteration, a worker goes through the selection, expansion, simulation, and backup phases. In selection, the worker repetitively selects the edge with maximum UCT value across all the adjacency edges of a node until reaching a leaf node. The expansion phase inserts a new leaf node under the selected node. The simulation phase runs a local simulation from the state represented by that expanded node using a random policy, and it returns a reward obtained from the expanded node. In the backup phase, the reward returned by simulation is back-propagated through the traverse path in selection, and it updates all the traverse edge weights. These four phases are repeated until reaching a limit x. X represents the maximum number of nodes in the tree. Upon the construction of the tree with size x, the agent takes an action with the maximum UCT value at the root, transits to a new state in the global environment, and start the process all over again with a new tree rooted at the new state. Next, we will discuss some performance issues with parallel MCTS that motivate our work. The most popular MCTS parallelization technique is the tree parallel MCTS, where multiple workers share access a single tree and expands different leaf nodes of that tree. To encourage workers to select different paths during selection, every time a worker selects an edge, a virtual loss is applied to that edge, and other workers landing on its parent node makes decision based on the new edge weight. This creates critical regions in the worker program that causes read-after-write dependencies between workers. As all the workers inevitably have shared access to the root node, in selection and backup, all the workers are serialized at the root by a latency interval. We denote this interval as T-sync. On CPU that is shared memory multi-core architecture, this interval is very large and severely hinders the scalability to large number of workers. This is because the tree nodes has to be communicated through the global shared memory, that is the DDR memory, and the interval for synchronizing shared access to a node is largely dominated by the DDR access time, that is usually hundreds of CPU cycles. The in-tree operations are largely memory-bound and cause the end-to-end latency of in-tree operations in selection backup linearly increase with the number of workers. On the other hand, simulations by different workers are completely independent, and parallel simulation time does not increase with the number of workers. We plot the time breakdown of entry operation latency as the blue areas and the simulation time as the orange area on a 56-core CPU, and we found that the entry operations take up to 75% of an entire MCTS step as the number of workers increase. This confirms that the interval T-sync lead to a performance bottleneck, especially for large number of workers. Therefore, our key objective is to minimize the interval between workers, thus improving the scalability of tree parallel MCTS system by taking advantage of the large and low latency distributed SRAM of FPGAs. Some questions associated with this goal are: first, for the system point of view, if we want to keep our system application agnostic and use CPU for simulation, how to reduce the negative performance effect of CPU-FPGA communication in the end-to-end implementation. Second, from the accelerator point of view, how can we ensure that we have minimized interval even with large action space that lead to large fan-out of the tree? We answer these questions in the system design and accelerator design. We first introduce our tree decomposition and mapping technique. We want to map all the computer memory components of the entry operations onto FPGA for high-speed performance and leave the application-specific simulations on the CPU for its general-purpose software environment. Assuming an application-specific state encoding of the environment is of size gamma. If we store all the attributes of the entire tree on FPGA, the memory requirement of the tree is tree size x times gamma, and the amount of data traffic between CPU and FPGA is number of workers p times gamma. We observe that the state attribute is only used by the simulation and does not affect the shape or other attributes of the tree. Therefore, we decompose the tree into two memory components: the upper confidence boundary tree, or UCT. It only stores the number of visits, reward information, and the UCT values of the tree and is mapped to the FPGA. The other part is the state table, or ST. It is essentially a list of the application-specific state encoding indexed by their tree node index, and this is mapped on the CPU. This decreases the memory requirement of the tree to order of X and make it portable to limited size on-chip SRAM. And it also reduces the communication overhead, since the only information to be communicated are the node indices and reward values. The CPU-FPGA system execution model is shown in this upper figure. It can be viewed as a bulk synchronous process with constrained communication at the end of each iteration. Specifically, a send and receive buffer is used for data communication, where a CPU thread must access the same index of the receive and send buffer to ensure the correctness of the tree update. The same rule applies to the FPGA worker data flow. The parallel program for each CPU thread is shown in the pseudocode on the bottom here. Note that concurrent accesses to the state table during state insertion do not require any thread-level synchronization such as mutex, because MCTS algorithm guarantees all the workers will expand different nodes, and any expanded node are different from any selected node. This means all the threads write into different ST entries concurrently. No ST read depends on the ST write of any other thread. Therefore, these ST operations will not become the bottleneck in the system throughput when increasing the number of workers. The high-level accelerator design is shown in this slide. We store the tree as an adjacency list. Each node entry stores a node and waits for all of its adjacency edges. The node entries are distributed in multiple banks according to a complete tree's topological ordering, where node entries of different tree levels are partitioned and stored in separate banks. The key idea behind this is to take advantage of level-by-level pipelining, where multiple workers can work concurrently on different tree levels. We also vertically partition the tree into different subtrees and let a root-level worker distributor assign the workers to different subtree pipeline at runtime. Because all the workers have to be serialized at the root level, we note that an important optimization for maximizing speed is to minimize the interval T-sync at the worker distributor. Apart from our bank partitioning optimization that ensures single-cycle access to all the banks, I will also talk about how to minimize the inter-worker interval at the root in an area-efficient way. Basically, given f edge weights, if we allocate a comparator for every 2 combination in f numbers and use the comparison result to sample from a pre-compiled comparison lookup table, we can obtain the maximum edge in 2 constant cycles. However, the area consumption of such a design is in the order of 2 to the power of the number of 2 combinations in F. This is not practical even for an action space more than 10. It's too large. Therefore, to constrain the CLUT size while keeping the interval small, we introduce a hierarchical CLUT design that divides the input edge weights into groups of size B and conquer each group of weights using smaller size CLUTs. This directly cut the exponential term down and make the design practical for larger fan-outs. For example, in one of the larger benchmark where there are 36 discrete actions, the tree has a fan-out of 36. A 2-level hierarchical CLUT reduced the LUT requirement by more than a billion times, only at the cost of 1 more cycle of each interval. Our experiments use 2 benchmarks, the Atari game Pong that has an action space and tree fan-out of 6, and the board game Gomoko that has an action space and tree fan-out and 36. The number of tree nodes in our experiments is set to 56K. All the platform specifications and the resource utilization is listed here. Now we show our experiment results. This figure shows the total latency of in-tree operations in one MCTS iteration for various number of workers. For the measurements on our CPU-FPGA system, which are the left columns, apart from the FPGA kernel latency, we also include both the total PCIe transfer time and the additional ST operations executed on the CPU for expansion. We see that for both benchmarks, the FPGA kernel performing in-tree operations on the UCT always have lower latency than CPU, and neither the ST operations nor the PCIe communication becomes a new system bottleneck. We also show that the FPGA speedups for in-tree operations scale well with respect to both fan-out and the number of workers. In this figure, the line plot shows the system throughput in terms of the number of simulation requests per process per second. The bar plots show the complete MCTS step execution time breakdown on the CPU-only and CPU-FPGA systems, where the bottom part of the columns are the simulation time, and the upper part column is the in-tree operation time. Consistent with our previous analysis, the total simulation time scales linearly with increasing number of workers and decreases with larger P. But the in-tree operations become the bottleneck and bound the achievable system throughput, as shown in the red line plots. As shown in the green line plots, our FPGA-based design largely alleviated this upper bound posed by in-tree operations and achieved a larger speedup with the increasing number of workers. Note that both line plots saturate at P larger than 128 because our FPGA platform only has 56 physical processors. So the scalability result is not obvious after increasing P over 56. However, if we were given a larger number of physical processors for simulation, the scalability result will continue to demonstrate higher speedups. To conclude, in this work, we propose the first CPU-FPGA system designed for accelerating tree-parallel MCTS that is application agnostic. Our system achieved higher throughput and better scalability to larger number of workers than state-of-the-art CPU-only implementations. There are many future opportunities in the area of MCTS acceleration. For example, one of our ongoing exploration is to explore the runtime dynamic SRAM bank management methodologies to better support arbitrary shaped tree growth at runtime. Another direction is to develop and explore the design space for deep learning guided MCTS using FPGAs for example, the AlphaZero algorithm. Thank you for listening. If you have any questions, feel free to contact me through my email here.